Welcome everybody to the special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to welcome deep learning pioneer and one of the most influential computer scientists, Professor Yoshua Bengio, to the Institute. Yoshua is a professor at Université de Montréal and the founder and scientific director of MILA. Yoshua's contributions to machine learning are so transformational that he really needs no introduction. Yoshua is, of course, known for his far-reaching contributions to deep learning, general models, and natural language processing. Among his best-known contributions are the identification and analysis of the vanishing gradients problem, gradient-based hyperparameter optimization with the implicit function theorem, curriculum learning, denoising autoencoders, generative adversarial nets, the first neural language model, and the first attention-based neural machine translation model. He is the recipient of the 2018 ACM-AM Turing Award, which is often referred to as the Nobel Prize of Computing, jointly with Jeff Hinton and Yann LeCun for conceptual and engineering breakthroughs that have made deep neural nets a critical part of computing. Additionally, he was ranked as the computer scientist with the most new citations as of 2018, and is a fellow of both the Royal Society of Canada and the Royal Society in the UK, as well as an officer of the Order of Canada, the recipient of the Quillen Prize and the Marie-Victorine Quebec Prize. Today, Yoshua will tell us about priors for semantic variables. Please welcome Yoshua Bengio.
Thanks. So today I'll tell you about what is essentially my current research program, and that covers a few papers that I will mention, but mostly a forward-looking discussion about what I see as some challenges as well as some opportunities for machine learning in the next few years. So if I try to look at what are the current limitations of vast machine learning methods right now, my impression is that our main weakness is with out-of-distribution generalization. And of course, you might ask, well, what can we do? It's not the same distribution. There's nothing you could say. But actually, humans are very good at that. And so it's interesting to ask what kind of tricks they might use in order to do so well out of distribution. Of course, for humans, it's not like the world was changing completely from one day to the next. Instead, they are able to capitalize on the things they already know and somehow combine those pieces of knowledge in ways that allow them to draw correct inferences in new settings. So one of the biggest, most important tools for generalization is compositionality, because when you're able to use some form of compositionality, you get a huge boost in generalization, at least potentially. And in fact, you know, it could be as good as exponential. So in earlier work, my colleagues and I showed that just the fact of using distributed representations could give you these kinds of compositional advantage. The fact of composing multiple layers on top of each other also provided that sort of advantage. That's a while ago. But actually, even though we formalized these things only like 6 years ago, it's really something that was in my mind at the end of the previous century and motivated, for example, my work on neural language modeling. So now one interesting question is, are there other kinds of compositionalities that we're not yet exploiting in deep learning? And the answer is, I think, lurking at us looking at language. Somebody's trying to tell me something? There. So, all right, okay. Let's consider systematic generalization, which is something that is being studied a lot in linguistics. For example, the way that we are able to combine new words in new meanings that didn't exist before. is interesting. But we can also do the same thing visually, for example, like in this image from Blake et al. And what's really interesting about this ability is that it allows us to see something about configurations of existing concepts that not only were not seen in the training data, but would have zero probability under the training distribution. So that's really the kind of powerful out of distribution generalization that we would like to have. And we can see humans are good at that. If I tell you a science fiction scenario that has zero probability under the training distribution of your life, you can understand perfectly well under hypothetical hypotheses that things do make sense. But more practically, you use this also in your everyday life. For example, if you move to a new country where traffic laws are very different, say driving on the other side of the street. But it looks like current deep learning isn't doing so well and tends to overfit the training distribution. This is not the same thing as overfitting the training data, right? And strangely enough, the more training data you have, the more you can overfit the training distribution. So if you're thinking about out of distribution generalization, adding more data isn't necessarily a good thing. So we need to better understand what is going on there. And so these papers are just, I think, starting points to just observe the phenomenon, but there's much more to be done. In particular, I think that we need to revisit learning theory in the case of the distribution generalization. We've been doing a lot of work on regular generalization within the same distribution. Now, you might ask, I mean, how could we ever say something like bound error on a distribution we have no clue about? And you would be right. The only way that you could say something about a new distribution is somehow if it had something to do with distributions you've already seen. So you have to think about maybe families of distributions or assumptions you're going to make about the way distributions change. And that's the sort of hypotheses that I want to talk about. Also, in order to be able to apply the knowledge you already have to new distributions, a very powerful concept, which really comes from looking at how we do it with language, is that we're able to break down our knowledge, like knowledge of the world is broken down into the knowledge we have for every word or phrase, and then in such a way, and then be able to interpret new things in such a way that even combinations that have zero probability can make sense. So the whole, it's not just like the objective function or the theory, it's also maybe architectures that come into play here. So I'll tell you about that too. And then the other thing, I'm already, when we look at language, the example I gave of driving, is getting inspiration from how humans might do this. Like the fact that humans are so good at it should teach us something. And maybe one of the most interesting observations in this respect is that when humans are confronted with a really new situation where they have to solve a problem, they have to act, very commonly they require their conscious attention. So in the driving example, you're driving in this new city, or a country where traffic laws are very different. You need your full attention on the road, and if somebody is talking to you at the same time, you'd be disturbed, and you don't want to listen to that. So there's something in the way that humans process information which seems to be different when we deal with those changes in distribution. That's really not like when we do our usual habitual routines. We have to think, and we have to focus, and we have to attend. So hence the connection to conscious processing. Another connection I want to make is with agency. So why would we have evolved an ability to deal with changes in distribution? And the answer would be because in the lifetime of a human being, there may be a lot of these changes. And so having the right priors, the right assumptions about the world, which somehow help you in many cases to deal with those changes, would be useful. So why would it be that we are faced with so many changes? Simply because we are agents. And when an agent does something, that may have consequences of the kind that yields changes in distribution and non-stationarities. And a very obvious place where you can see this is if you have multiple agents. So you might think if I'm alone, then I don't disturb things too much in my environment, that somehow there's a sort of stationarity. But if there are other people and they act of their own volition, it's very hard to pin down a single stationary distribution, because typically things will continue to change due to the agents and their interactions. Now, psychologists have been actually thinking about this issue, that there seems to be two different kinds of mental processing for, like the examples I gave of habitual tasks versus those that require your conscious attention. And one such categorization is called the system 1 versus system 2 division. And the idea is system 1 is everything you do intuitively, quickly, and that you don't need your conscious focus on. It's not that you are unconscious when you do it, but you don't have conscious access to how those computations are taking place. And those computations are taking place in a highly parallel way. And when I say non-linguistic, what I mean is that it's hard to translate into words what is the sort of computation that is taking place. It doesn't mean that language doesn't call upon system 1. And of course, everything you do in a routine way, habitual way, usually falls in this category. Now, it's interesting to also think about the kind of knowledge that is being represented in this way. And for the most part, the kind of knowledge that is being called upon in system 1 is implicit knowledge. So what does it mean? Well, it's connected to the fact that it's hard to express that knowledge. Sometimes you can, sometimes it's harder. Sometimes you can have only a bit of a summary of it verbally, but often, for example, if consider a Go playing master, of course they can talk about their play, but it's just the tip of the iceberg, and a lot of the knowledge is not known consciously to them, which means they can't explain it to someone else. And that's why it's not enough to read a book about how to play Go. You have to practice. So a lot of that knowledge comes out of practice, and practice is essentially what machine learning is. So current deep learning especially is good at system 1 tasks, but not so good at system 2 tasks. So these tasks, system 2, are usually require more time to be performed. They can seem to involve our abilities to reason and reason logically. Usually they involve multiple steps in parallel. And of course, you can consciously explain what you're doing during the time you're doing it or after. This is the kind of task that is involved in things like planning, reasoning, or programming. Everything algorithmic is a description of a sequence of such steps, similar to how you would think about a problem. And that kind of knowledge is explicit. We can verbalize it, and we can teach it to others just by explaining it. They don't need to practice it necessarily. So that's system 2, but of course, many interesting cognitive abilities, including language itself, calls upon both. So the pictures showed my driving examples, just to keep in mind what this is about. And since we're good in machine learning right now, the first kind, I think it's important to start thinking about the second kind. but in a way that preserves what we have achieved with the first kind and looks for systems that can do both of these things in a synergistic way. Now, what's interesting about system 2 is it has this combinatorial property that that we were talking about at the beginning, right? That it allows us to manipulate these high-level or semantic concepts that we can verbalize. That's what semantic is about here. In ways that mean that on the fly we can like recombine them combinatorially in new combinations to solve new problems. So one aspect of this, which goes back to the title of this talk, is around the kind of knowledge. So as I said, the two systems seem to call upon two different representations of knowledge. What I'm hypothesizing is that maybe it's not a coincidence. Like maybe the kinds of things that is most associated to system 1 and the kinds of things that are associated to system 2 call upon different sorts of priors, making different kinds of assumptions about the data that or the information that is being manipulated with either of these systems. So so then, why would it be the case? Usually we think of priors as covering, the whole distribution. Our distribution has these properties, and we'd like to build, say, machine learning algorithms that take advantage of these properties. But typically, properties that we assume about the world will be too much, like too strong. They won't apply to everything. There will be a lot of exceptions. Or they might even only apply to some aspects of the world. And so if that was the case, if you had a set of properties that work well for some parts of our knowledge, then it would make sense to have a sort of subsystem that is able to take advantage of these properties to handle that kind of knowledge, and another subsystem that doesn't require these assumptions, but can cover the rest of the knowledge. So that's a hypothesis I'm making, both about human intelligence and potentially machines we could build using this that same structure. Okay, so a lot of my talk is about trying to, and my current research is about trying to explicit some of these priors, some of these inductive biases that humans may be exploiting, and that we could also put in machine learning. So I'm going to go through most of these in my presentation, but let me give you a quick high-level rundown, and we'll dig a little bit deeper then later, so you will have an idea of what I'm talking about first. So the first assumption is about the decomposition of knowledge into small pieces. For me, this is a fundamental thing about system 2, that we are able to break down knowledge into these independent pieces, and each of these pieces involves very few of these high-level semantic variables corresponding to words or phrases. So that can be formalized, right? We can say, well, oh, that means a joint distribution, if it was represented as a factor graph, was sparse. These dependencies, these underlying factors that relate variables together, there is very sparse. Very few variables are connected to that factor. Okay, so that's an assumption, and convince yourself that it's a reasonable assumption. Well, it's very easy. Just look at language. A typical sentence involves very few words. A typical sentence can be like one such piece of knowledge. Ergo, that's kind of a proof by example. Now, another thing you could deduce by looking at language is that these variables that we'd like to populate our big graphical model of system 2 knowledge, they have to do with causality. At least many of them have to do with causality, and in the sense that words typically point to what? They point to agents, like people, animals, entities which act. They point to other entities that the agents can control, like objects. And of course, objects can cause other objects to do things. And then they point to how cause and effects are related. The actions themselves, like the verbs, the modes, where and when, and all that. And things like planning to do these things, intentions, and so on. And of course, many other subtleties that we express with language, but often boils down to the core is talking about causal variables. And of course, when you want to talk about cause and effect, just only speaking about the graphical model is not sufficient. We have to somehow represent these causal structures as well. The third bullet point is maybe one of the most interesting ones and maybe more surprising ones, because it speaks to the out of distribution issue that I talked about at the beginning. And I said two things about the out of distribution issue and systematic causalization. I talked about how the world changes, how the environment of the distribution changes, and I talked about reusing pieces of knowledge. So the first two things, the first two bullet points are about breaking knowledge into pieces that can be recombined easily. And the third one is about how things change. And here we're going to draw a little bit on the second assumption. So, for a long time, of course, people studying causality have been thinking about interventions. Interventions can change the distribution. I mean, the basic property of causality is that it helps us figure out what would happen if somebody did an intervention, right? And so, if the world was governed by these changes in distribution due to agents doing things, which is essentially the situation that agents are in, maybe we can take advantage of this assumption that the changes are now local in the right representation space where, like say, one node of the big graphical model gets to be intervened. So that might be a big clue to help us deal with changes in distribution. The next bullet point is something I've kind of already assumed almost in my definition of what these high-level variables were when I talked about the connection to language. And it's the idea that these high-level concepts, which we represent somehow in our brain, they are related to words and phrases. That maybe it's even like a very, very simple mapping. Another assumption, which comes out of, again, thinking about language, but also thinking about things like classical AI, thinking about programming. So now it's about knowledge representation, and so this big graphical model, we're gonna break it down a little bit in its properties. And it has a sort of parameter sharing attribute in the sense that you have these pieces of knowledge which we might call rules that refer to variables. Like if I have a piece of knowledge about dogs, it works for your dog and my dog. And so so it's not like a graphical model where you have separate parameters for each of the factors. You may have the same factor deployed over many tuples of instances of objects, right? So this is exactly why we have arguments in programming, and this is why we need indirection in programming, and we need variables and so on. So we need to bring that in the structure of that knowledge representation. Of course, we want to do all of these things within a neural net framework because your brain is a big neural net. We already know how to do these things in programming in classical AI, symbolic AI. We want to put in these inductive biases in neural architectures. The next inductive bias is also connected to changes in distribution, but now it's something maybe more related to all of the current work on meta learning. There's the idea that, oh yeah, we have changes in distribution, but there are things about the world which are stationary. I mean, in the sense that eventually learning these things would converge, right? Whereas the non-stationary aspects of the world, there is no point in trying to learn them in a stable, permanent way, because they might change in sort of arbitrary ways. And so you'd like to be able to separate the things that are converging and stable and robust to changes in distribution, like invariances, from the things that might not benefit from these properties. So one way that's very obvious in that respect, in the way that I'm thinking, is the mapping, which could be a two-way thing, between perceptual input like pixels and low-level actions and these high-level semantic variables. I am betting that that encoder decoder thing is highly stable. Of course, you can add a new concept, but the others don't change that much. They can be refined because you learn more, but what changes is the relationships between these things. I learn a new fact and can be learned very fast. I learn a new phone number, bang, I can remember it for some time, and I don't need a lot of practice. But those that encoder is something that requires a lot of time to converge, right? So it's stable, but it also means it's also more part of system one. It needs practice. You don't usually learn a new concept unless it's a immediate composition of things you already know. Otherwise, it takes time to learn. The last bit, I don't think I'll have time to cover in my talk, but I'm going to say a few words about, is related to many of the things above, in particular to causality, but it's connected to learning and credit assignment. So if you observe how humans at the conscious level perform credit assignment, it also has this property of requiring very few elements. So when I infer like an explanation about something, I can provide the explanation in one sentence or a few sentences. That means the kind of causal chains that my conscious processing is able to process at this explicit level is very short. It's just a few hops. If it had 1,000 causal elements that I had to chain one after the other, probably I wouldn't be very good at it. And so maybe this is also something we can take advantage of, at least to understand, to learn the kinds of things that humans are good at learning at that explicit level, and doing credit assignment or inference over. Okay, so that was like a summary of the whole thing. Now we can dig a bit deeper. So here's the first assumption, which I started talking about 3 years ago, and I kind of already explained. It's saying that knowledge is represented by a bunch of little pieces. These pieces correspond to dependencies between a few variables. That's it. And we can see that in sentences like, if I drop the ball, it will fall on the ground. Now, one thing to note, compared to a lot of the recent literature in unsupervised representation learning, is that these high-level variables, which are connected by this sparse graphical model, they're not independent of each other. They're not marginally independent of each other. So ball and hand are not statistically independent, right? They come together in a particular way. So there was some interesting evidence for this, in addition to just thinking about it from the language point of view, coming in the analysis of deep CovNets and deep, especially deep unsupervised neural nets like GANs, where what you find is that the high-level variables, which under the GAN are independent, typically don't have a meaning. In other words, humans can't pinpoint a single name for these units at the top level, because the GAN assumes they are independent. But if you look at 1, 2, or 3 layers downstream of those generative latent variables, you find units which humans can put a name on. And so what this suggests to me is that we don't have the right structure here. We should not assume that the top variables that are the ones that are interesting are independent, but instead that they would have this highly structured kind of dependency that we need a prior on them, which is not factorized, but instead maybe like this sparse factor graph. All right. Oh yeah, I want to say a few words about attention here. So what does it have to do? What does this assumption of sparsity? What may it have to do with the way humans reason over that graph? Now, there are many algorithms we know to reason over graphical models, but some of them would naturally go, if they were sequential, they would naturally go and visit one of these factors at a time, maybe 1 or 2 factors that are connected to each other, in trying to usually find configurations of the variable that are consistent with observations. This is what inference really is about. And so if you were to do inference in that way, you would need an attention mechanism that selects a few of these variables and the factors that are connected to each other in the graph to do your inference. And it feels like your thoughts are ways to create coherent interpretations between the variables that are in your mind at the time when you're thinking. And so I think that reinforces the idea that a lot of what we're doing with thinking is this inference over this very large graphical model in order to find explanations or guess interpretations or imagine things. So attention, of course, as many of you know, has been at the heart of a lot of progress in the last 5 years in deep learning, especially almost everything having to do with natural language processing. But it's not just a question of, oh, it's new architecture that helps. But I think there's something fundamentally different. And I think that attention is a key to deep learning shifting from being able to only do system 1 things to being able to do system 1 and system 2 things. So in particular, instead of operating on vectors, we now operate on sets. And if you think about what you have in mind as a set of objects in our neural nets, they're represented as key value pairs. It makes a lot of sense. Okay, so now up to now it was all kind of intro, and now I'm going to talk about a few papers that are derived from these ideas or are driving the progress of these ideas. One of them, this recurrent independent mechanisms, I think was presented the last ICLR, and but really was conceived almost 2 years ago. And it's connected to a really interesting notion from the literature on causality, the notion of independent mechanisms. So the idea of independent mechanisms is that different pieces of knowledge that concern cause and effect, like how a cause influences an effect, are independent, not in the usual statistical sense, but in the sense of the information about these mechanisms, how they work. So if you had a parameterization for these mechanisms, the information in one mechanism doesn't tell you about another. So that's a starting point for this paper, and as well as others I'll talk about later. In this paper, we did something very simple, no like obvious connection to causality. It's more about modularization of knowledge. So we take a regular neural net architecture, and we break it down into modules, where within each module you have a full connectivity, instead of having the usual full connectivity at the scale of the whole network. But now we're going to use attention mechanisms to control the way that the modules are talking to each other. And then the other thing is we're going to be creating a sort of competition between those modules so that only a few of them are allowed to speak at the same time. I'm not going to go through the details, but weird attention mechanisms of the kind you find in transformers, you can do these kinds of things very easily. What's interesting is that just changing the architecture in this way seems to yield better out of distribution generalization in set of problems that we studied in that paper. Okay, so yeah, a bunch of experiments. These could be used inside reinforcement learning benchmarks like the Atari benchmark and yield some advantage over regular recurrent nets. Oh yeah, I want to say, I should have put that slide earlier. I want to say a few words about the inspiration we can get from neuroscience and cognitive neuroscience. Consciousness is still a kind of taboo word in AI, in machine learning, and even in computer science in general. And it's too bad. We are late, guys, because our friends in neuroscience have had the taboo in the previous century, but they moved away from it thanks to imaging techniques in the brain that have allowed neuroscientists to see that actually different things are happening in the brain depending on whether you're conscious of them or not. And so they've started to map out in what ways is the processing different. And there are a number of theories now to try to explain how conscious processing is different from unconscious processing and how they combine with each other, of course. And one of those theories which receives, I would say, most of the attention is the global workspace theory. Now, a really interesting property of this theory, which also makes a lot of intuitive sense, is that the brain is composed of many modules. So this is like the modules in the previous paper I mentioned. And although they all act in parallel, when they want to communicate with each other, they have to go through some sort of bottleneck. So you can think of it as a working memory or a blackboard. Or the scene of a theater is an analogy they also use. The modules that are temporarily selected can broadcast information to all the other modules. And that information is the information you currently have at your consciousness, right? That you're in your mind at this moment. And so that creates a sort of bottleneck, which has all kinds of interesting properties. And I think a lot of the work that we're starting to do in my group, but also in other groups now, in machine learning might help us provide a machine learning justification. Like, why would you have such a limitation in yourself? Like, it seems crazy. Humans have such a big brain, and we only have these few bits that can go through our consciousness. It's crazy, right? There's got to be a good reason for this. So this is, I think, something that we will resolve in that the synergy between the research in machine learning and the research in neuroscience can help us figure out in the next few years. One way to think about this is when you use your imagination, every part of your cortex potentially can participate in this. But for the imagined scenario to make sense, the different pieces need to coordinate with each other. And so the values that are being instantiated in each of these modules need to be coordinated. Otherwise, you'll have something incoherent, right? They won't choose values or variables that are consistent with each other. And so the fact that we have this only a single simulation machine creates and we don't have full any-to-any communication. It just wouldn't be feasible. Maybe the reason why we need this bottleneck for coordination across the brain, which is huge. If you think in terms of like how many neurons there are between one place and another place. It's incredibly huge. The brain is huge. Okay, so inspired by this theory, and as a follow-up to the RIMS paper, we have a paper just submitted that in addition to having these modules that are tightly connected within, but sparsely connected to each other through attention mechanisms, we are going to make the attention mechanisms sort of force to communicate information through this working memory or blackboard, if you want. So only the modules that are activated in a sort of competition, just like in normal attention mechanisms, you have this competition, softmax, right? Only those that are selected are allowed to write in this memory. So this memory is just a bunch of slots and key value pairs. But everyone is allowed to read from that memory. And that simple architectural change really helped the RIMS do even better compared to things like regular LSTMs, and in particular out of distribution. So this is interesting, but I think we still need to understand better the why this could be helpful. Another recent paper that's ICML is about using attention mechanisms not just at the conscious level, but also at the lower levels. So we know there's a lot of work in cognitive science and neuroscience, for example, of how we, even in V1, the early stages of visual processing, already there's some attention mechanism at play, which are going to make us interpret images even at that low level, depending on the context and depending on top-down signals. Like I'm sure, so I'm sure you noticed that the H and D and the A in cat have exactly the same shape. It's just context here that makes a difference, or that the image on the right could be interpreted either as a rabbit or as a duck, right? If it looks on the right, it's a rabbit. If it looks on the left, it's a duck. And your brain will alternate between one or the other, and it will interpret the low-level structure as well. And so we try to incorporate this sort of thing in the RIMS architectures by having a hierarchy, just like we have in the brain, like a deep learning hierarchy, but where we also have top-down signals. And then we use attention mechanisms to decide, within a particular module, whether it wants to pay more attention to the information coming from the top, which is the context, or the information coming from the bottom, which is like from sensors. And what's cool, let me just skip this. Yeah, it works in experiments, but the really cool thing is this. So if you increase the amount of noise in the input, then dynamically the attention mechanism will start giving more weight to the information coming from the top, which makes a lot of sense. Your input contains less and less information, so you have to rely on your context and prior to interpret the input. So about causality, so of course that's connected to agency, right? If you want to study causality really in a setting that's more like AI-ish, really you have to connect it to agency and how we can change the world through our actions. One of the early hypotheses I made a few years ago is that a good representation of high-level concepts should be related to how we can independently control the different aspects of the world. But that kind of information can only be discovered if you can act in the world. It's hard to discover by just watching movies. So here's a picture of the sort of architecture that we want to discover. This has been in my mind for a long time in deep learning. Like the original goal of deep learning was about learning good high-level representations. And I now think that these high-level variables are essentially causal variables, and they are semantic variables. So semantic meaning we can talk about them. Causal means they have a causal interpretation. By the way, not every variable has a causal interpretation. So if you make your graphical model have as variables the pixels in an image, you'd be hard pressed to find cause and effect relationships between pixels. There isn't, right? And so really you have to map the data to the right space before it becomes meaningful to think of those variables as having a causal interpretation. So we need to discover at the same time how these high-level variables are connected to the raw inputs and outputs, and how these variables are related to each other in a causal way. And we also need to figure out how those variables can change under the interventions corresponding to actions of events, of agents, okay? So that's the program. And then in the service of that, let's talk about how these distributions at the high level can change due to interventions. Okay, so I've already talked about the independent mechanism hypothesis, but let me get back to it because it's really interesting. And it's kind of thinking that's not what you normally associate with just standard graphical models. So remember I said that the hypothesis of independent mechanisms states that the information in one mechanism, like one of these conditionals in the top level graphical model, doesn't teach you anything about another one. But as a corollary, if one of these conditionals gets changed, for example, by an intervention, you don't need to change any other conditionals in order to account for that change. Of course, the values of the variables may change as the consequence of the causal structure, but you don't need to change the parameters, right? So that's cool, right? In other words, if we have the right space for representing these variables, we can quickly adapt to changes in distribution because the change is going to be localized. So few bits of information are needed to account for that change. As an example, if I put on dark glasses, my visual system, distribution at the pixel level is going to be completely modified. Every pixel is different. So if I'm representing the knowledge at the level of pixels, this would be terrible. I might have to retrain from scratch my whole model. But of course, this would be the wrong thing to do, right? If you're able to map the pixels to a better representation in which there is one bit that says I'm putting on my dark glasses, right? Or one variable which controls the general lighting or something like this, then I can explain that change very easily. I can infer what it was with zero data if I have the right model, or if I need to discover about what happens when you put on glasses, I may need just a few examples. So this is what we want to exploit, right? So now we have to think about these changes that are localized, and we need to, unfortunately, we may have to discover both the encoder that maps things in the right space, as well as how those variables are related to each other to take advantage of this. But it could go the other way around. So if I assume that the world is like this, that changes is localized, I could learn about a good representation, both the encoder and the graphical model, because that solution is the one that's going to make my sample complexity in the face of changes in distribution minimized. Okay, let me give you an example of that. So this is a paper from a year and a half ago. I guess it's the first in that line. No, not quite. It was the one in 2017. But it's, for me, it's one of the most important papers, and it was, yeah, it was at IKEA this year. Consider the simple problem of having just two random variables, a and b. And you can either factorize a joint as P of A times P of B given A, or P of B times P of A given B. Now, the question is, if there is an intervention and somebody changes the value of the cause in particular, we get a new distribution, a new joint. Now you have to adapt to that new joint. It turns out that if you have the right factorization, right in the sense that it corresponds to the correct causal structure, then you can adapt faster. And we now have some theories, some theorems about this. It's not always true, but it's generally true that you're going to have this property. But it makes sense. And so the intuition is, if, let's say A is the cause, and I have the correct factorization, P of A times P of B given A. Now, somebody changes P of A on me. P of A has only a few parameters. It's because it's only a marginal, right? P of B given A didn't change. It has a lot of parameters. It's like n squared instead of n. So I only need to adapt n parameters. The distance in parameter space between my old model and my new model is small. And so I can adapt quickly in terms of SGD steps. On the other hand, if I had the wrong model, that's what the figure shows, the number of examples versus the true expected log likelihood of the different models under the change in distribution as they adapt with examples. So if you have the right model, this is the blue curve, it learns quickly and converges. The wrong model eventually also reaches the same asymptote, but takes more time in terms of number of examples. And the reason it takes more time is simply that if I assume that it's P of B times P of A given B, and somebody changes P of A, well, unfortunately, P of A seeps into both P of B. Like if I change P of A because of Bayes' rule, it's going to change P of B, and it's going to change also P of A given B. And so now I have to change all my parameters. That's terrible, and so I need more data to learn. Right. So if you have the right model and if you have the right encoder, so we can do the same experiments where you don't observe A and B directly, but now you observe X and Y, and there's a simple relationship between A, B, and XY. You can recover the up to permutations, symmetries. You can recover the AB causal structure as well as the relationship between AB and XY using the same principle. Yeah, this was what this slide was about. And we extended this kinds of ideas to larger graphs, introducing a parameterization that's efficient for the belief over all the possible graphs. The problem now is that the number of graphs, that you need to consider, if you don't know, which is cause of which, you have to figure out each of these edges, whether it's present, and if it's present, whether it's in one direction or the other direction. So that's exponentially large. So that seems hard, but we have an algorithm that does a reasonable job. In fact, better than any other known methods, as far as I know, to recover the underlying graphs up to, well, I guess, sorry, no, I don't have that figure. Anyway, up to graphs of like 50 or dozens of nodes. I see time is flying and I haven't covered everything, but I think I've talked about everything that mattered. Oh yeah, that one is cool. So that's another recent paper submitted. Remember I mentioned one of the assumptions that we should factorize our knowledge into reusable pieces where, like the rules in classical AI with variables. And that means the same rule could be applied to multiple variables. So it's like a parameter sharing in the graphical model. So in the world of RIMs, we can achieve this by decoupling the weights of a module, which are like these recurrent weights, from the values that they operate on. Okay. So now the same neural net which represents an operation like a rule or a statistical dependency, can be applied to different objects, for example, in the same image, or the same object, like here, these characters in a video game. At one moment, they could be driven by one rule, which is one little module. At another moment, they would be driven by another module. So the rims have this ability to pass these object p-value pairs from each other. That's already there, but it didn't have this factorization where we separate the object files, as they would call it in cognitive neuroscience, from the schemas or the rules. And we can easily do that, but now we have to do a kind of double attention over, which module should be working on which variable. And when you do that, you get advantages again on out of distribution generalization. Sorry, I'm not going to explain the details. I don't have the time, but trust me when the paper comes out. There's a last paper I want to mention quickly in the last minute or so. I mentioned meta-learning at the beginning. Meta-learning is about learning at multiple timescales. I worked on this in the early 90s with my brother, and we were thinking mostly at that time about evolution. That's kind of a kind of learning at a very slow timescale, but within one evolutionary draw, one individual genetic code, there's a life of an individual where the individual also learns. So that's one way to think about meta-learning. And what is happening during that life is computing the fitness that matters for the evolutionary scale, right? So so we can, this is a huge amount of work in machine learning in the last few years. And it's used a lot to deal with changes in distribution, multitask learning. And I think there's a nice connection to the whole discussion we've had in terms now, not of architectures, but of what is a good objective function when you have these changes in distribution. And so we've also done experiments with these modular recurrent net, the RIMs, where we make some of the parameters, the attention parameters, be meta parameters, so slow learning, and we make the internal recurrent weights be fast learning. And we find that combination, and not the vice versa, leads to faster adaptation to new tasks in a curriculum learning setup. That's something we've worked on called the Baby AI tasks a couple of years ago. So that's also another recent submission. And that's it. I've drawn here a little graph to help us see that I've talked about a lot of subjects which may seem unrelated to each other, but actually are related to each other. So out of distribution generalization, yeah, of course, it's connected to non-stationarity. It's connected to meta-learning. Maybe less obvious to some people, it's connected to causality. And maybe also less obvious to some people, it's connected to modularity and compositionality, which is connected in linguistics to systematic generalization, which is connected in cognitive neuroscience to system 2 and attention and consciousness and reasoning, which is connected in AI in general in the notions of indirections and variables. So lots of interesting connections. Turns out these are not completely separate topics, but they have deep links with each other. Thank you.
All right, let's thank Yoshua for the thought-provoking talk. So we have 2 questions from the audience for now. The first question is from Howard Rees. The question is, how do your meta objectives that presume simplicity, for example, short causal chains or sparse factor graphs, apply to low rank completion or even recommender systems? Are they related at all?
Are they related? So, I mean, clearly low rank assumptions are assumptions, and so they're maybe part of a list of priors. I mean, there is a sense in which we are able to explain, for example, a lot about a current scene, focusing on only a few variables. So that feels a little bit like a low rank thing, but I think it's different. It's different because we pick some factors that we want to focus on, and we ignore a lot of things. But we do it in addition, we do it in a dynamic way. So usually in a low rank factorization, we statically choose some factors that are going to be more important and dominant to explain the data. But here we may pick different things. So our attention can select different aspects depending on what's relevant in the context, or what fancies are mine.
Okay, thank you. The next question is from Yasser Dahal. The question is, so how would the initial model weights affect the inductive priors that you learned?
Right. In fact, we know that a lot of the priors that biology puts in the brain come in the connectivity, the initial connectivity. And that's what allows us, for example, to learn to see with our auditory cortex if we're born with some visual deficit. To some, I mean, it's not perfect, but to some extent. And so you can think of the modular architecture constraints and the attention constraints as some of these architectural priors, which could be adapted with learning rather than being fixed. I haven't really explored this direction. But if you ask your question about in our experiments, how do initial parameters matter to the result? Not very much, but this is not very new. I think for most deep learning, there's quite a bit of stability across retraining for different initialization. There's a bit of variance, and it actually could be exploited to learn about a bit of the uncertainty, but it's not a lot.
Great, thank you. So the next question is from Rohit Goswami, but I think I'm gonna call on Rohit to ask the question verbally because it seems a little unclear. Rohit, if you can unmute yourself, that would be good.
Oh, right. So the shortest one is, could you clarify what the zero probability cases are? And like, does that just mean cases which don't show up in the training distribution because, but are still valid in that parameter space, or are they just invalid parameter combinations which will never be part of any kind of distribution, training distribution?
No, it's the first case. So there's one of the papers I cited and didn't have time to explain from my colleague Aaron Corville. They created a systematic generalization problem. In the training distribution, they have pairs of objects in an image, and in the training distribution, they only take a subset of all the pairs, right, that can be matched. Right, and then they have a test distribution out of distribution where some of the pairs which occur with zero probability under the training distribution can happen. Right, and so if you don't see a lot of data and you have an architecture that is modular, well, you are actually going to have not such a big gap between the two distributions. But the more data you see where, like, let's say the letters and the digits never come together, it's either pairs of letters or pairs of digits, then you kind of learn the rule that a letter never goes with a digit, and so you give zero probability to that, and if it happens, you're kind of, it's like your neural net is completely screwed. But somehow humans are not like this. They can still entertain something out of distribution, right? Because Because in the meta-learning way, right, they've seen this. They've seen that they were used to something and then it turned out it was wrong.
Yeah, but in some sense, shouldn't we just be then putting a low probability? Like, in fact, the problem is that
Sure. Yeah, if you're Bayesian or anything, you'll never put zero probability on anything if you can.
Yeah.
What I meant by zero was maybe provocative, right? But and I think it would still work even with zero probability. But yeah, of course, but if you put a very small probability on these events, you would still have trouble. Like you would still be not able to generalize properly. I mean, not necessarily, but at least this is what these guys observed in their experiments, and a number of other people have done similar experiments.
All right, thank you. The next question is from Anupam Madhurata. The question is there any connection between causal graphs and knowledge graphs?
I guess there is. I mean, the semantics are obviously different, right? So knowledge graphs usually are focusing on, you can think of it as a factor graph where you only have pairs or triplets of variables, right? So, you know, item X is a Y, right? So that's like an attribute. It's a pair of things, and you're going to have item X and Y are connected by relation R. That's a triplet. So these sort of dependencies, in a way, they form indeed a sparse factor graph. I think we can entertain more or a higher order than 2 or 3. But it's fascinating that in knowledge graphs, you're able to encode so much knowledge only using 2 or 3 variables at a time. And by the way, sometimes it's inconvenient and people like have to play tricks in order to encode dependencies that should really involve 4 or 5 or 6 things, but yeah. But usually in knowledge graphs, you don't have causal arrows that says, the relationship between X and Y is of a causal nature where X is the cause and Y is the effect. If you have that sort of knowledge in the knowledge graph, then in a way you could think of it as a causal graph, right? Now, the way we structure a causal graph, usually, at least the structural causal models, which is the standard notation for them, is through conditional dependencies, conditional probabilities. And knowledge graphs don't always have that structure, but you could, in principle, convert them to that.
Thank you. The next question is from Kevin. The question is, when you try to learn the sparse latent graph structure and the encoder network, what objective function do you use? Is the maximum likelihood across multiple data sets? Are these data sets generated from your true model by perturbations in the latent space? If not, how do you get empirical data sets that differ in small but causally relevant ways?
Right. I'm not sure what is the right objective function to use. This is one of the open problems. In the experiment I talked about, we kind of cheated by avoiding the problem by making the transformation an invertible transformation, a rotation. Okay, so that was kind of an easy case. So see, the problem is, if you do maximum likelihood on the top level variables to learn their joint, and you optimize the encoder for that, well, the encoder would have a field day just learning the constant output, because that gives infinite likelihood to your model. Yeah, so there are ways around. So for example, we've been doing work on contrastive objectives that are now becoming used a lot in unsupervised representation learning. So I think that might be a way to do that. But frankly, I don't know what is the right way, where you want to jointly learn about the encoder and the distribution at the top. in principle, you could also use things like in variational autoencoders, which is likelihood at the pixel level. But I don't like likelihood at the pixel level at a philosophical level, because it forces us to pay attention to a lot of unnecessary details. And it's not clear then that the high level will be doing the right thing. I don't know. I don't have like a very good answer to give, but I suspect it's not the right solution either. I mean, mathematically it's clean, but I'm not convinced it's the right way of doing it.
Can I ask a follow-up? Yeah. So what about, so if you have maximum likelihood across multiple diverse data sets that share some things in common, then intuitively, like if I overfit the pixels of my first distribution and then I shift it slightly, then I realize that I must have the wrong graph structure, right? So I'm paying attention to the shadows, but really what's the shadows are this noise, and I recognize that it's noise because the second distribution has different shadow patterns, but the structure of the shapes is the same. Yeah. So I'm wondering, like, I haven't seen much work on like unsupervised meta learning. I'm not up to speed with meta learning. There's so much to follow. But intuitively, like if you carefully control the ways these distributions are related and different, then maybe max likelihood is enough. That's what I'm curious about.
Maybe.
I mean,
I'm not convinced. Like, I don't know really. Like, I'm agnostic, but just my aesthetics tell me that it's got to be that the objective function should pay more attention to what is going on at the high level. Mm-hmm. But maybe pure maximum likelihood would do it. I mean I think it would do something reasonable. Let me tell you a story about this. So a few years ago in my group, we developed some of the early neural nets for speech synthesis, text-to-speech synthesis. And one of the issues there is you have a huge discrepancy in number of bits of information at the low level, acoustic samples, and at the high level, like phonemes and words and stuff. So it's about a 1,000-to-1 ratio in terms of number of bits. Now, so why is that a problem? So if you do maximum likelihood, there's like, it's like out of 1,000 bits that you're going to pay in the likelihood, there's one that's important for the high level interpretation. And so of course, if you had a perfect maximum likelihood thing, it would eventually find that one bit correct. But it's going to be drawn in the noise of the 999 other bits, which don't really matter for representing the high level of the structure. That's the concern. And we seem to observe that in experiments. I don't have a proof of this, but yeah, I think it highlights something that may be fishy. And so you might say, oh, let's just put more weight on the stuff on top, and then it's a hack. We need something better.
Yeah, like power bays and stuff like that. Yeah. No, yeah, it's an interesting open problem. Cool, thank you.
Can I ask a follow-up question? I guess one issue with meta learning in a lot of the formulations is just, if you were to use the same objective at the base and the meta levels, it is equivalent to essentially having a much bigger model, right? Where you just, decompose some parameter space. I wonder if you have any thoughts on, whether the meta objective should in principle be very different from the base objective, or whether they could be similar.
I think for humans it is different, right? And there's a practical reason which you can see in reinforcement learning, right? So very clearly in reinforcement learning, people will cook up proxies for the reward, which are short-term. So it's just from an optimization perspective. The things that you want to optimize over the long run, the slow time scale, might be the ultimate thing you care about, but it's usually difficult to optimize them in the fast time scale. And so you end up with these proxies. Think about exploration rewards in reinforcement learning. It's an inner loop thing, right? We don't need it in the outer loop. We need it in the inner loop. And so, yeah, I tend to think that you want to have different objectives.
Thank you.
And probably you want to learn. I mean, you can be really smart and find the right inner objective, but you might, you might learn it, and some papers have done that in meta learning,
right,
in meta RL.
Mm-hmm. Thank you. So the next question is from Seth Stafford. The question is, have you thought about Gary Bozarsky's good enough brain concept? So his notion is that system one responses might come from a subnetwork of highly connected hub neurons and provide more flexible responses. Some additional attention mechanism is needed to engage or recruit a fuller response. Mainly wondering if you're familiar with it, and because it is another very interesting angle on system one versus two.
I'm baffled by the number of papers I need to read, and I didn't even know about this theory. So clearly I have to pay attention. So I can't say much about it, but
I'll see if I can dig up a good link for it.
Oh, that'd be great.
Just send you. Yeah, sure. Thanks a lot.
All right,
Great
thank
talk.
you. The next question is from Sumia Deep. The question is, when you say transforming the image data space to a different space in which you would make an invariant to say lighting, are you saying those variables should be hand designed?
No. I mean, of course, if you knew the right invariances, you could cook up some of them in your system. That's what a lot of computer vision is doing. And I'm not against that in principle. It's just that what I'm interested in is discovering kind of higher level principles which allow learning to discover these invariances. And when I say invariances, I don't mean necessarily like the way we think about invariances in computer vision. I mean properties of the world which are stable. And of course, that gives rise to what people in computer vision call invariances. So this is the long, what is the knowledge that is shared across tasks, across the whole lifetime?
All right, so the next question is from Joshua Pan. The question is, I understand your other system to inductive priors, but what do you mean exactly when you write shared rules across instance tuples requiring variables and interaction? Are these referring to the encoders or / common representations?
These refer to the high level representation. So in our paper, when we do this, we don't really think much about the encoder. So the encoder is some like convnet or something. And then on top of that, you have the recurrent nets, which we think of them as doing inference over the implicit graphical model that we're not representing. And so that those shared rules, they're really about the high level knowledge. They're not about the encoder. I mean, maybe there is also interesting structure in the encoder, but we were focusing on the property that we know from language, logic, and all that exists at the level of semantic variables, which is these shared rules.
Thank you. And we have one question from Punyan Shamshidi, who can ask the question in verbal.
Hi, sure. Thanks for the talk. So my question is related some intrinsic property of us as human. So we sort of have interesting flexibility. For example, we can switch between many different tasks, right? In a short period of time. We can put together even like programs of behavior we have never executed or seen before, right?
Right.
This task. My question is related basically to your particular work. You presented many different directions, but I was wondering which one of those directions you see as a hopeful direction that can basically make AI like human in that sense, in the sense of this flexibility that I mentioned in particular.
Well, pretty much all of the things I've talked about, like all the papers I cited, were aiming at that. many of them had this decomposition of knowledge into small pieces. So right now we have two tracks in different papers I've talked about and are going on in my group. There's the declarative knowledge representation where we have an explicit graphical model. So here the pieces are the conditionals or something like that. And then there's the, if you want, inference representation where you don't have an explicit representation of the graphical model, but you have the mechanism for combining the pieces together for answering new questions. And that's the RIMS, the modular architecture, recurrent architectures, and so on with attention. And so I think that, well, it's in the second kind that we can see the dynamic recombination of new things happening. In the declarative knowledge, yeah, you still need to specify the mechanism by which you're going to do inference, and it is that mechanism which is going to, on the fly, do the reasoning, do the inference that is going to select a few pieces of knowledge that are relevant to solve a particular problem. Whereas with the RIMS, with the RIMS, you're learning the inference machinery itself, and then you use attention mechanism for doing that. So in a way, it's closer to what we think the brain might be doing. I don't think the brain has an explicit representation of like this knowledge graph or this graphical model, but it's pretty close to it because we're able to have access both to the declarative knowledge, at least the conscious level, and to do inference on it. And so one interesting question is, how do we do both in a way that's consistent? There are several, possibilities that are interesting. But anyway, to go back to your question, the key property is just attention, right? It's just the thing that allows you to select this module or this piece of knowledge and then combine them to solve a new task.
And one follow-up question, I would love to hear your thought about this different direction about compositionality, somehow like different slightly from your work, like the work by Joshua at MIT, right? Joshua Tannenbaum, about the clever, this kind of framework, which they thought about composition and it's slightly different from attention and
yeah. I mean, they're trying to hardwire a lot of that prior knowledge. I'm trying to hardwire only very general principles that are in this kind of priors. But let me add one thing that's maybe going to help to clarify how the modular structure helps compositionality. It's not just the modular structure, it's how the attention mechanism creates a communication channel between the modules, where this communication channel is sort of universal. Right? So remember, we have this broadcast mechanism and these key value pairs. Now, what this means is that you can swap in one module for another module to do a particular job. In other words, any module can talk to any other module the same language. So there's like a lingua franca in the brain by which different parts of the brain are talking to each other. In our implementations, this lingua franca are these key value pairs that can be produced as output by these RIMs, read by any other RIM, and because the attention mechanism is selecting from any RIM where the input comes from, it forces all the modules to speak the same language, so long as they get connected at some point during training. That will force them to speak a sort of compatible representation of these implicit objects represented by key value pairs. So that's how you get the exchangeability that leads to combinatorial generalization.
Thanks a lot.
Thank you. And the next question is from Anushka Singh. The question is high level. So the question is, what do you think about GPT-3? There are a lot of concerns about it being too smart on Twitter. What are your views on it?
I don't know. I haven't tried it. I'm not too excited by this kind of research. I mean, it's cute, but I don't believe that we can take our current machine learning and scale the size of the model and the number of examples towards infinity and hope for miracles. Of course, it's going to get better, but like it doesn't answer much more interesting and fundamental questions like how do humans learn a new task with like 1 examples or 5 examples or something. How do humans adapt to these changes in distribution? Right? That GPT-3 is not helping me with that, right?
And if I,
sorry, doesn't it scare you to like look at all the videos where it has generated so much text and it just responds like it's a human? Like looking at all of that, that's all I've seen, like the whole buzz on Twitter. It's scaring me. I mean, I am like a whole practitioner of machine learning, but
apparently there are also like examples people have come up with where it fails utterly, right?
Oh, so that's your defense, because it fails, it's not that good?
So I think there's a fundamental reason why it's going to fail. And the reason is that it doesn't, so it's one of the slides I skipped, sorry. It was about grounded language learning. So remember at the beginning of my talk, I said that there are aspects of the world that we can represent in the explicit realm of system 2, like in language. There are aspects of the world which we don't, and possibly we can't. And so if you read an infinite amount of text, eventually you will potentially cover all of the system 2 knowledge that humans can communicate with each other. But you will never capture the system 1 knowledge, at least the parts that are not talked about in text. So in other words, there's a lot of things that you and I know at an intuitive level that we can't express with language, and no machine that only reads text will ever have access to that knowledge. And that knowledge is important to actually understand language. So language needs system 1. Like to do real language understanding, you have to understand what the words refer to. And the words refer to the whole thing, not just the part of the knowledge which is in these rules, for example, but also the part of the knowledge which is in these big system 1, like convnets, whatever, that can't be put in words. And so I think there's a fundamental limitation to the approach of training only with text. Of course, it's going to fool us because we're going to imitate. So what it does is it imitates natural language text, right? And it could be very, very good, but I don't think it has it will always have like it will have like dead angles because of it's missing that intuitive knowledge.
Thank you.
All right, and if I may ask a follow-up question. So earlier in your talk, you alluded to the fact that inferring the right causal structure will enable better data efficiency. And
Yes.
wondering what your thoughts are on this, recent research paradigm of increasing the amount of data and compute without really, trying to design the model in such a way to, enable better data efficiency, and whether that's driving the field towards perhaps a local optimum.
Yeah, I mean, and also it's driving the field towards somewhere only like super big, rich labs can do anything. Like, I can't experiment with GPT-3. I mean, yeah, probably if I put enough money from my grants, I could like run it for a few seconds. But I'm much more interested in the problems that academia can look at, and maybe they don't need that much compute power. I mean, of course, if we want to ever build something that's going to have the sort of computational capabilities of human brains, we're going to need a lot more computational capabilities than we currently have. But that will come. Like, hardware people are working hard on that, and they're making a lot of progress. And I think in 10 years from now, or 20 years from now, we'll probably have enough compute power to match the human brain. But if we don't have the underlying conceptual and theoretical and algorithmic tools to, do a good job, not just computationally, but also statistically, or if you want, in terms of generalization and all that, I don't think it's going to be sufficient. And really, the heart of machine learning has always been about assumptions, right? About priors and inductive biases. The main reason why I was pushing deep learning in the early 2000s, was because I thought that state of the art of the day based on kernel machines was using two weak inductive biases. The only inductive bias was essentially smoothness in the one form given by a kernel, and that you needed extra inductive biases in order to move up the ladder of better machine learning. And so I think we're going to continue doing that. We're going to add assumptions that humans use or may not use that give extra power to those machines. But if we can find inductive biases that cover a lot of the things in the world that humans care about, then we can build machines that are on par with human intelligence and can have a discussion with humans.
Thank you. And we have another question from another member of the audience. The question is also high level. To what extent did work like thinking fast and slow inspire ideas for research versus provide a retroactive way to frame your work?
It's a bit of both. So I guess I started thinking about conscious processing just by myself, by introspection. And then I thought, well, I should read more about this. And so I did. And now, for example, I'm reading a lot about the global workspace theory that I mentioned in my talk. There's a lot of work in neuroscience, in cognitive science, that can teach us a lot and give us a lot of inspiration beyond like the simple intuitions. It's not enough to just do introspection in this case, precisely because there's a lot of what is going on in your brain which you don't have access to. And so you want to look at what neuroscientists see by their experiments where they go beyond introspection.
Thank you. Are there any more questions? Okay, so if there are no more questions, that concludes today's seminar. Let's thank Yoshua again for the very thought-provoking talk.
Thank you. Thanks for your questions.